Hello friends, we start with our next topic. Our next topic is known as initial conditions. So as you know about initial condition, one of the toughest topic in network system. Okay, so now we are going to understand about what is initial condition and how the problems of initial condition will be solved and what are the different type of techniques applicable in initial conditions. So that we will go through and we'll try to understand it. Before going for this video, I have already mentioned about my previous video of capacitors and inductors. Please go through it because the concept of capacitor is largely applicable in initial condition. The concept of capacitor as well as inductor both are applicable, but you will see the concepts of capacitor is largely applicable in initial condition. So still you have not subscribed, like and comment on my channel, please do it. Once you subscribe it, it will be more easy for you to go through my all previous video in a sequential manner. So we start with this topic known as initial condition. So we will see what are the subtopics we will say under initial condition. So let us first understand it and then we'll go one by one and we'll try to understand the concepts of initial condition. If I talk about initial condition, the topic which we are going to cover under this is, first we'll talk about the RL and RC circuit, RL and RC, or you can say I'll talk about RC and RL circuit. First we'll talk about the RC circuit, then RL circuit. RC circuit we will see without any excitation. Without excitation, I should write it here as without excitation. It means when no source is applied. Similarly, RL circuit also when no excitation is applied. Now we will see again RC and RL circuit when some excitation is applied. Okay, or you can say with excitation. So when some excitation is applied, so under what is the behavior of RC and RL circuit under that condition that we will see. So these are the four subclasses we will see under the initial condition, very important, and based on analysis of these four we will see how the initial conditions is solved in the network. Further when we'll go, we will see all these different type of condition and then we'll go through the problem solving sessions. So what are the different type of problems we'll see under this topic. Then we'll talk about the conditions, that is t equal to 0 plus. I will explain you everything, but just for the time being you try to understand what are the different topics which we are going to cover under initial condition. So these are the first four, then problem solving sessions we will see, and then we will see the problems and the condition when at t equal to 0 positive. You will find there are certain type of question in which the question will consist of either you have to solve the voltage or current or the differential of voltage or the differential of current at t equal to 0 plus. So we will see how this condition is applicable and how the problem will be solved with this condition. Okay, so this is our another topic under initial condition, that is t equal to 0 plus. After that we will go through the problem of RLC circuit. Okay, we will see the RLC circuit conditions also. Okay, when resistance, inductor and capacitor all are connected. Under this RLC circuit we will go through the Laplace transformation technique. Okay, we will see the initial condition with the help of Laplace transformation technique also, because in some of the problem you will see by applying Laplace transformation you can easily solve the problem. So that we will see. Also we will see little bit about the signals. Okay, signals, it means your del t, ut and rt. Okay, so these are the three type of signals: your impulsive signal, unit step signal and ramp signal. So we will see a little bit about del t, ut and rt. Okay, so more or less we'll cover all the different type of concept under these topics, and then we'll try to understand one of the difficult topic of network. Generally whenever you go for networks, so you just came to know that yes, initial condition is a little bit difficult topic, but once you follow my all videos under this topic, you will easily able to understand how the initial conditions problem used to come and how we solved it. We will see all different problems of competitive examinations also here. So this is you can say it's a long going session, or there are a lot of videos under this initial condition, and my request to all of you, please follow all those videos one by one. So first we start with the RC circuit under the condition without excitation. We are going in this manner. Okay, so first we start with the RC circuit without excitation. Okay, now as I said, we start with the RC circuit analysis. And in this RC circuit analysis, we will simply understand what is RC circuit when no excitation is applied. So this is the condition when no excitation is applied. Very important, just keep in mind. So we will understand what is the behavior of an RC circuit when no excitation is applied. Okay, so I am just considering one simple RC circuit consisting of one resistance and one capacitor. Okay, this is your circuit, this is your ground portion, this is R, this is C, and here you can just say some current I is flowing. So when some current I is flowing, definitely some voltage is appearing across the capacitor, and that voltage is what? It is V. Now the very important thing is we have to analyze the condition of RC circuit, and we'll try to understand why we are analyzing RC circuit. Okay, so we are analyzing RC circuit under no excitation condition. It means when no voltage is applied. That means here in a special condition I am considering that this capacitor was initially charged. Please keep in mind the very important thing. This capacitor was initially charged by a voltage known as V0. This I have considered. The meaning of initially charged we will more understand through this diagram. Please try to go through it. Here I am taking one switch. This is your C, this is your R. Okay, and this is your switch. See, we understand all the conditions of T. You have seen in your networks: T equal to 0 negative, T equal to 0 positive, T equal to 0, T equal to infinite. Okay, there are all different conditions. We all try to understand this, so don't confuse with it. For the time being, I'm not going to explain all those conditions, but here I am considering that this capacitor is initially charged. As in my previous video, I have already explained you that capacitor is an element which is actually not dissipating the energy, it is basically converting the energy. That means it stores some energy at some time instant, and after some time instant it delivers that energy to the circuit where it is connected. So for the timing, if I consider that capacitor is initially charged, and at T equal to 0 when this switch is closed, now this capacitor starts discharging, okay, through the resistance which is connected along with this capacitor. Okay, so this is a simple condition. Now we will try to understand how that phenomena will take place. So here I am considering these two nodes A and B. Okay, so these are the two nodes A and B. If I apply KCL at node A, so what is the KCL at node A? Here is the current, here is the current. So if this is the voltage V appearing here, so you can say that C dV upon dt, the current across the capacitor, plus V upon R, that is equal to 0. Okay, that means you can say this current and this current. Forget for the time being the direction of the current, since it is a simple KCL I am applying here. So I have considered that yes, these two current, that is C dV by dt plus V by R, is equal to 0. So if you solve this equation, it is simple differential equation. You can write it as 1 minus RC dt. Can you write in this manner? Yes. If you integrate it, just integrate it. So while we are going for the integration, we have to consider some limits. So as I said that capacitor is initially charged by some voltage V0, and this is a voltage V at which we are considering the voltage which is appearing across capacitor C. So the limit here is V0 to Vt, since it is a time dependent voltage across the capacitor, which I already explained you. So here the limit will goes from 0 to t. Yes, because I have considered that initially it means, say at time t instant t equal to 0, some voltage exists, that is V0. So that limit goes from 0 to t for finding out the solution of V0 to the function of Vt. Very simple. So if you solve this integral, that integral comes to be what? That is ln of V with the limit. You know about the mathematics, so I don't think there is any issue. Minus 1 upon Ct with the limit 0 to t. Okay, so once you solve this, I'll directly solve it. This comes to be ln Vt upon V0 is equal to minus of t by Rc. Yes, okay, and if you replace this, so that comes to be Vt upon V0 is equal to e to the power minus t by Rc, or from here you can say that the value of Vt comes to be V0 e to the power minus t by Rc in volts. Okay, so this you can say is the voltage across the capacitor Vt, that is V0 e to the power minus t by Rc. Very important solution of voltage across the capacitor in a circuit where no excitation is applied and your capacitor is initially charged by some voltage V0. Very important expression. So this is just a mathematical expression, so it is not that much difficult, you simply understand it. Now we will analyze what this expression actually. Okay, so here your Vt is V0 e to the power minus t by Rc, it is in volts. Okay, so if I draw this diagram, say this is your Vt with respect to your time t, and if this level is V0, so this is the exponential delay, this is the exponential decay. Okay, so friends, this is your Vt. Okay, this is your Vt. It is simply V0, this voltage V0. Okay, this voltage V0, and now after that at t equal to 0, when we have find the solution, that comes to be V0 e to the power minus t by Rc, and this is the curve. Okay, this is basically decaying exponential. Now what this diagram explains, if you try to understand this solution which we have find, this solution we have find when this switch is closed, that is t equal to 0. Okay, that means if you talk about this condition, the initial voltage across the capacitor was what? It was V0. Yes, it was V0, or you can say that was a constant voltage. But what happened when this capacitor, it means the initially charged capacitor, when connected to a resistance, or you can say some load R, what happened? This capacitor starts discharging. Okay, this capacitor, or you can say the voltage across this capacitor, starts discharging through this resistance. So if you analyze the discharging curve, so this is your discharging curve. It means after t equal to 0, whatever the solution is coming, now this voltage got discharged. Okay, so from here we one thing which we understand that yes, if capacitor is initially charged by some voltage, after some time it got discharged when it is connected across a resistance R. So now the important point comes to be, what is the mechanism of discharging? I mean, the important term comes to be here is known as tau, which I called as time constant, okay. So if you see this term, that is e to the power minus t by RC, if I consider this t by RC is equal to 1, it is at the condition when t is equal to tau. So you can say that the value of tau comes to be RC. Yes, the value of tau comes to be RC. You can say that the value of tau comes to be RC. This tau is known as time constant, and this is a time constant of an RC circuit. Very important expression. So that means if you put the value of t by RC as 1, so this E will become e to the power minus of 1, okay, or you can say it is V naught by E. Okay, let me solve it here. If this t upon RC is 1, that means the value of Vt is equal to V naught e to the power minus of 1, or you can say Vt is equal to V naught by E. If you solve it, this comes to be 0.368 of V naught. That means at some value of t that is equal to RC, that means tau, you can say this value is tau, okay. This value is tau. What happened? The corresponding value at Vt, falls to a value of 0.368 of V naught. If it is a unit value, so from here this value falls to a value of 0.368 V naught at t equal to tau, okay. So when your actual output falls from this value to a value of 0.368 V naught, or you can say it is 36.8% of your original value, whatever the time present on your time axis is basically your time constant. So this is the definition of a time constant. So you simply say that when your response will fall by 36.8% of your original response, whatever the time at your time axis, that is tau, is known as your time constant, and it is represented by tau is equal to RC, okay. So if I see little bit about the graph of time constant, please try to understand. So friends, as I explained you about this So friends, as I explained you about this diagram, and I mentioned as tau as your time constant, from this expression if I say Vt upon V naught is basically e to the power minus t by RC, or you can say it is e to the power minus t by tau. So if you put the value of t, please see here, if you put this value of t as tau, 2 tau, 3 tau, 4 tau, 5 tau in this manner, so you can find the different value of Vt upon V naught here. So I have just find those values. Why I find, just try to understand it. For t equal to tau to 5 tau, if I am putting this value, just see these are the response. Initially it was 0.368, then it was 0.135, then 0.049, 0.018, 0.067. It means if you try to understand, I am redrawing this graph, okay. So from here, if you again see, say it is Vt by V naught, and this is your time axis. So what happened when you put 0.368, this is value of tau and this is your corresponding value, and as you increase the value of t from tau to 5 tau, see that value comes to be 0.0067. That means this value is almost comes to be 0, almost comes to be 0. Okay, that means at time t equal to 5 tau, this response goes almost to 0. If you see this value reflect, it is almost goes 0. If I write here as some equivalent sign, so that shows that the value of Vt upon V0 almost goes 0, or you can say your response goes 0. It reflects that your capacitor fully discharged, and once your capacitor is fully discharged, your output response goes 0. That means at 5 time constant, very important thing, please keep in mind, at 5 time constant capacitor either discharges or charges. Very important expression. So just keep in mind this, I am writing here, at 5 time constant capacitors fully discharge, capacitor fully discharge or charge. That means at 5 time constant, when the value of expression goes 5 time constant, the capacitor will get fully charged or will get fully discharged. Very important thing. So this you just keep in your mind. Sometime this question directly comes. So just keep in your mind that the capacitor will be fully discharged 5 time constant. Okay, this is one very important expression, very important expression. So from here we will understand that yes, the RC circuit in which no excitation is applied, and if initial voltage of V0 is existing across the capacitor, after some time it gets discharged, and the discharge curve will follow an exponential decay, and at 5 time constant the capacitor will get fully discharged and your output response goes 0. Okay, so this is all about the RC circuit. We will little bit more understand about the one graph. So friends, this is our next graph, and we will try to understand, as I mentioned earlier, about V is equal to V0 e to the power minus t by RC, where RC is time constant, so we consider as tau. So if I write it as V upon V0, so that is e to the power minus t by tau. So this is basically this response. So from here, for different value of time, if you analyze the value of time constant as 0.5, 1 and 2, you will find that these are the different curves. When you talk about tau equal to 0.5, this is the curve. When you talk about tau equal to 1, this is the curve, and when you talk about tau equal to 2, this is the curve. What this curve explains? The meaning is, as the value of time constant increased, here it is a lower time constant, now here it is a higher time constant, here it is a more higher time constant. So we will see that as the value of time constant goes increasing, as the value of time constant goes increasing, the decaying of the exponential graph is in this manner. What it explains? So that means a circuit with a small time constant, with a small time constant has a faster response. That means this is tau equal to 0.5. You will see this red curve, this get decayed earlier as comparison to this green curve. Similarly, this green curve as comparison to this black curve will get decayed earlier. So that means as the value of time constant is small, the response of the circuit is faster. Okay, so here the statement is, as time constant is smaller, the response of circuit is faster, or you can say the output will decay as early as possible when you compare it with the time constant which is higher than this value. Okay, so you can say that a circuit with a small time constants give a faster response in that it reaches its steady state. Now here one word is coming known as steady state. There are two different type of state. One is known as steady state and another one is known as transient. So we will understand both these terms in detail, but for the time being just try to understand that as the value of time constant is smaller, the response will be faster, or you can say this curve will decay early as comparison to the value whose time constant is higher. Okay, so see, this is a lower time constant and the circuit gets settled down as early with comparison to the value whose time constant is higher than this value. Okay, so this is all about the concept of time constant. The meaning of term known as steady state, it means once this graph will settle down, it reaches to a constant position. That constant position is basically known as steady state position. Okay, so we will more try to understand about steady state and transient. So for the timing here, it is clear that the time constant is smaller, the response of the circuit is faster, and it decays as early as possible. Okay, so this is all about the RC circuit. So from here, one more important thing is coming is in this type of condition where no excitation is applied, we have seen that some response is existing at the output. So this response is basically referred as natural response of the circuit. Okay, this response is referred as natural response of the circuit. This is known as natural response. Now the another word coming as natural response. So why I am talking about the natural response? Because there is no excitation in the circuit. Circuit behaves as per the voltage which was previously appeared on that capacitor. So you can say that this is a natural response. So this is referred as natural response. So for the timing, I will just explain you. We will talk about natural response and forced response. Okay, this is first point. Then we will talk about steady state, then transient. Okay, then we will see zero state, zero input in terms of response. Okay, so natural response, forced response, steady state response, transient response, zero state response, zero input response. So these are the 6 terms which used to come here, but for the timing I am only talking about the natural response. And natural response, as of now you understand that when no excitation is applied, the circuit behaves naturally, and this was a natural response of the circuit when no excitation was applied. Okay, so this is all about the analysis of RC circuit when no excitation is applied. In my next video, we'll talk about the RL circuit analysis when no excitation is applied. Okay.